Hello everyone and welcome to this first tutorial of Transform 2021. Very excited to have you all here, and we are super pleased to have Pygimli giving a tutorial here at Transform 2021. Pygimli started in the early 2000s during the PhD project of Carsten and Thomas, and some 10 years ago Florian joined the project, and just 10 days ago Andrea joined the project as well. And we are very excited to have all four of them here giving you a tutorial about how to use Pygimli and get out the most of it. Make sure, if you follow live on YouTube, make sure to join the Slack channel on Swang. You will get their support from all four of them if you have troubles installing it or following it along. What else is there to say? Nothing. Florian will start the show and he will lead you through the tutorial. Enjoy.
Thank you very much. We are very happy to be here. We want to start by thanking the organizers, so Matt Hall and his colleagues, for putting this wonderful community together, and in particular to Dieter Wertmüller, who onboarded us and went through the technical trial with us, which was already live streamed accidentally. But now this is the real thing. We want to talk about geophysical modeling and inversion. And we will do this in a hands-on manner with Pygimli, a software package that has been developed for 2 decades now. And while Thomas and I will be presenting today, Carsten Rücker is really the backbone of this project and has written most of the code. And we are very happy to have Andrea Balza just joining us recently. Her fresh perspective was really tremendously helpful in the preparation for today. And we are very much looking to her future contributions. And there are many others, Maximilian Wagner from the University of Bonn, who contributed a lot to the induced polarization part, complex valued inversion in the last time, and Nico Skibbe and Friedrich Dinsel, you know who you are. So warm welcome, thank you to all the other contributors. A warm welcome to everyone who's watching live and who will be watching this in the future. You can find all the material under this link, transform21.pygimli.org, and Thomas will show this page in just a second. So what is Pygimli? It's generally an open source, flexible modeling and inversion library for geophysical problems. And it comes with structured and unstructured meshes in 2 and 3 dimensions, and with the management of these meshes. The computationally more expensive part is written in C++, and then we have boost Python bindings to the complete C++ library, and this makes it very flexible, but at the same time very runtime efficient. There are various ready-made geophysical forward operators, some of which you can see on the right-hand side of this slide, for different geophysical problems, and it comes with a general Gauss-Newton type inversion. So this is a deterministic inversion framework, and it has very flexible means of combining different data sets, so in the frame of joint or constraint inversions. And it has a region-specific regularization, meaning that you can, if you have prior information, you can define different starting and regularization options for the different subsurface regions. It's open source, platform compatible, and we also use it a lot for teaching and reproducible research. And the 1.0 version was published in 2017 in Computers and Geosciences and has been picked up quite nicely by the community. A little bit on the software architecture, because the software architecture also builds up our outline today. So we built up on a number of very powerful dependencies for visualization. We use VTK, Matplotlib, PyVista recently, mesh generation, triangle in 2D and Tetkin in 3D, but we also have interfaces to Gmesh and in particular Mesh.io, where you can basically load in any mesh from outside, and then hopefully also the subsurface integration in the near future. And on top of that, we have Pygimli, and the very basic level would be the equation level. And Thomas will start with that later, where you can basically solve a partial differential equation on a user-defined geometry. On top of that, we have the modeling level. So this now already includes the physics for the given geophysical problems, different types of forward operators. And on top of that, we have the so-called application level. And this upper high level is probably the entry point for most users. So if you have a data set, you want to load it, you want to pre-process it, you want to invert it, and visualize both results and data misfit. So what we will also do later. This is the way to start. And these three different levels will also be discussed today, starting with the mesh generation and the equation level. So this will be our outline for today, starting to build a subsurface model, solving a partial differential equation on that very model, moving to the modeling level, so taking the same geometry, but then solving a geophysical problem, in this case, Crosshole travel time measurements. And then we will have a 10-minute break, and we will continue with the inversion side of things. So the first half focuses on modeling, and then we continue with inversion, introducing both two geophysical managers, the Traveltime manager and the ERT manager, applied to synthetic and field data. And then in the end, we will explore a bit more what is possible, how to move forward from here, and also demonstrate the integration with other packages, so to build your own custom-made inversion. And yeah, with that, I'm very happy to hand over to Thomas.
Hello, good morning. A warm welcome also from my side. Can you hear me? And can you see my screen? Yeah. Okay. The main entry point for pygimli is the website pygimli.org, where you can look up several things. You can look up tutorial examples. We go into details about that later on. Main source of information will be the AP documentation, where you find all the different models that we are going to use in this tutorial. But now we come back to the transform tutorial, and we straight go to the transform page. It's a GitHub page where you can find all the Jupyter notebooks that we're going to use today. You can git check out from here. You can download the notebooks by yourself, and you can start. There's also installation instructions, and but we are not going to do this installation right now. You can do that, and in case of question, you can direct yourself to the Slack channel, and people will have you to do that. So that's the table of contents, and there's some installation stuff, and I just want to quickly dive into. So assume you are having your conda installation ready, everything is prepared. So I'm just starting from I'm a Windows user. I'm just starting from the starting menu and a kind of a PowerShell prompt, and this is located somewhere here. And what I have to do is to activate the transform. So I'm typing conda activate pg minus transform, and now I'm in the environment that should have everything that you need today for this course. And if you never going to work with this environment, I usually go to the Explorer, where I have checked out it. I'm copying the path, going here into the console, changing directly to this path, and then calling Jupyter Lab, and then I'm ending up I like here, and this is what you all can do, and we will do everything from scratch. So we will start creating a new notebook and typing things like a equals 1, and then it will be automatically run. So that's the point, and now Florian will start with the first notebook on creating meshes.
Yes, very happy to do so. So I'm in a clean notebook here. I copied the one that was distributed, but there's not much copied except the heading and the objectives of this notebook. So in this notebook, we want to talk about how to create a subsurface geometry and a mesh. And we will also talk about the differences. But first, discretizing the subsurface is always a very important and first step. We need to define parameters, and we also want to discretize model parameters for the inversion, maybe also dependent on the resolution of our geophysical method. And we will talk about geometries and meshes and explore the pygimli mesh tools. Also, the link to the documentation is provided here. We won't cover all of this, but hopefully give you an idea on how to build your model from scratch. Then we will talk about unstructured meshes, predominantly in 2D, but we also have 3D capabilities, and I will also demonstrate that the transition from 2D to 3D is relatively straightforward. And and finally, we will demonstrate the possibilities to modify, visualize, export, and import different meshes. Okay, so ready to start. And we always start with the very first line, which is importing pygimli as PG. This is our shortcut. And today we will be using the mesh tools a lot. So I will also import the pygimli mesh tools as a separate module and give it the shortcut MT. This just saves us some typing throughout the run. And then we will start by creating a subsurface model, a geometry. And the very first part is we define some values. So let's say we have the left corner of the model, which is at minus 30 meters, the right corner at 30 meters, so 60 meters in total length, and then we also have a depth of 25 meters. So these are just Python integers, or floating point values, of course, are also possible and make more sense here. And then I use this information in a kind of a hello world. So create world is the function where we start with a lot, which creates the geometry and also comes with some information on boundary conditions, for example. So we can define the lower left and the upper right corner of the geometry. So the or the upper left and the lower right is also possible. So I will use the left and the surface at y equal to 0. I also have to define the end keyword argument. And just in case you never worked in a notebook before, what is really handy is if you have a function that you will be using. So create world. I did a small typo here, sorry. So this is the function, and if you do Shift tab within the brackets here, you will see the function signatures. So what type of arguments do we need to provide to the function? And the ones without the default arguments, so without equal to something, these are the ones which have to be specified. So they are non-optional, and this is start and end. And then there are many others we can define. And so start and end are mandatory, and then we will have a look at the others. And we define the depth here in the so negative y values. Okay, and important is then to give this thing a name because we want to reuse it later. And we have a very high-level generalized show function which can visualize many different objects. And we will use that PG show function to visualize the world. And it will return the matplotlib axis, and which we can just mute here. So this would just be our rectangle, which we start filling with more interesting objects now. So one thing that we could do is we could provide horizontal layers as a list of depth levels. So I could put a layer here at 5 meters depth. If you type mesh tools and then create and press tab completion, you will see many different functions to define geometrical objects, in particular in 2D, but also a lot in 3D. And again, we have a lot of import and export functionality for other more sophisticated 3D mesh generators. And what I will do here is create a line. With create line, I also provide start and end of this line, and I can also show it just like I showed the world before. And the nice thing is now that I can add geometrical entries. So I can say that my overall geometry, which I want to use later, should consist both of the world and the line that I just created. And again, I'm using pgshow to visualize this geometry. And note that it automatically makes a third region because we added this line, and this now intersects this lower layer. And we have defined the region markers on top, so layer 1 and layer 2 at the bottom. We haven't defined anything particular for the middle layer, so this has the region marker 0. But in the end, these are just numbers which we use to populate the mesh later with physical properties. And we will show you how to do this in the following notebooks. Okay, so let's make this a little bit more interesting. I think a very flexible function for creating mesh geometry is create polygon, where you can basically specify a number of points which are then connected and optionally closed into any arbitrary shaped objects. And here I'm just using 3 points. So a triangle basically. And I'm calling this a geological body, some anomaly of geophysical properties in the subsurface for our synthetics here. Okay, so if I visualize this, it has 3 points, and these could be topography points, for example, could be an interface within the subsurface. But if I really want this as a triangle, I have to specify that the geometry should be closed. So then it's a closed triangle, and it also gets a region number which I can specify. And since I already used everything from 0, 1, and 2, I will give this the region number 3. I can also add more nodes along the edges, for example, like this. And then I have to make sure that they are also visualized. So with the pgshow, could take an argument of show nodes, and we set this to true, so it also shows the intermediate or the nodes that this geometry has. So I can play around with this. Now I will stick with 5, and then to make this a little bit more smooth, a little bit more interesting, we can also add an interpolation to this, and I will use the spline interpolation here. So this will smooth these objects. Should smooth these objects. Oh, it's interpolate. Sorry, it's not interpolation, but interpolate. Again, you can check the keyword arguments by pressing Shift-Tab, and there tells me interpolate is the keyword argument and linear is its default value, but I'm using spline interpolation here. And this gives me this object, which I can then also add to my geometry. So I can do something like this, adding the body to the geometry and showing the resulting geometry in the end again. Okay, and this will be our geometry that we will be working with throughout the rest of this tutorial. But this is just a geometry. So basically it's a geometrical definition of boundaries, of regions, but it's not a mesh yet. What may be a bit confusing in the beginning, but is that we treat everything internally the same. So if we print the geometry, it tells us it is a pygimli mesh object, but it doesn't contain any cells. So it's just a geometrical definition of all the boundaries and regions and the nodes. But it's not a mesh yet that we can use for finite element simulations or parameter estimations. And how do we get from the geometrical definition to the mesh will be then the next step that we discuss here. Maybe another thing that I should note, because you saw that already contains a lot of boundaries, and you see the region markers here. The geometry also contains boundary markers, so I can visualize them by boundary markers equal to true. And this will visualize the marker numbers, and very much as we can specify physical properties to subsurface region, so to region markers, we can specify initial conditions, so directly or other type of boundary conditions to these boundary numbers, and Thomas will demonstrate this later on. Before we can simulate, we need to create the mesh, and the important function here is also within the meshtools package, and it's called create mesh. So this is the function we will be using it in Jupyter Lab. If you put a question mark behind the function, you also get the documentation, and a very powerful tool or very general feature of Python is that it's open source, so you can also put a second question mark, which will give you also not only the function signature, but also the code behind it. So you can always see what is happening behind the curtain. And this create mesh function takes our geometry as the very first argument. So this is a piecewise linear complex. So the first object here. And I will call this the mesh, which we will be using in the following. And I can also visualize it with the pgshow high-level function. Again, pgshow is capable of showing many different types of Python objects, or pygimli objects, and it basically then distributes to the individual show functions. So we have pg, and this comes with a viewer interface, and then we have in 2D MPL and PyVista in 3D, and this has a show mesh function, and if pgshow gets a mesh, it basically distributes to that function and also passes on the keyword arguments, and there are a lot of settings that we can use to make nice figures. Okay, but I will be using pgshow here just because it's a bit shorter, but keep in mind it's just an entry point. And this can take the mesh, and this would be with default settings, so just calling the triangle mesh generator and populating the geometrical object which we defined earlier, and accounting for these boundaries and the objects we defined. If we want to do finite element simulations with this later, then we also need to be aware of mesh quality. So we want to avoid sharp edges. So we need a high quality mesh also to get the for high numerical accuracy. And also when we do an inversion, we also have to be aware of our mesh, because each triangle would represent a subsurface parameter, and we want these parameters to be to be according to the resolution of our method. Okay, so we look at the keyword arguments that we can specify here, and the first thing is quality, and the quality basically represents the smallest allowed angle within each triangle. So if I would set this to a very low value, let's say 5 degrees, then I would get a very low quality mesh. I can increase this further. So this doesn't look much different, maybe 20. We see to achieve a quality of 20, so to have angles which are at least larger than 20 degrees, we also need more cells. So the quality also scales, correlates with the number of cells which we have in the end. And some reasonable values are usually between 33 and 34. Maybe I'm going with 33.5 here, which looks like a nice quality mesh, so nicely shaped triangles. And there's also a tutorial on the website which showing also how to calculate and how to visualize mesh quality. Okay. Another thing, if we have a high quality mesh, we also need to be aware of the number of cells we have. And this can be specified with the area keyword, which is basically the maximum allowed area of each triangle. And if I put this to a high number, then nothing will change here because it will still need to satisfy this quality factor. And to get the quality, it needs some cells. So it doesn't affect anything if I'm having a larger number here, but it will affect if I'm using a smaller number, because then I'm specifying the maximum cell and it still needs to obey this quality criterion. One last thing maybe is to use the smoothing. So it calls an additional smoothing algorithm of the mesh generator. So, and this looks like a pretty nice mesh that we can use in the following. And we will pick up on this mesh, and you also have it within the Git repository. And you can save the mesh with the save method. And we just have to provide a file name. So we can just save it as mesh.bms. And the geometry is a little bit different because we also need the geometrical definitions of the boundaries and the regions, and then we have the export PLC function, so exporting a piecewise linear complex, which takes the geometry as the first object, and then also file name. So I'm just calling this geometry, which you can then reuse later. Okay, so to the interest of time, I will go to the ready-made notebook that you also have available and talk a bit about mesh modification. So how can we modify the mesh we created? And one first thing would be translating mesh. So I'm doing a copy here. I'm calling pgmesh, which basically just creates another instance of the mesh so we can keep the unmodified version of it. And the mesh comes with different methods. And one method would be translate, where I can provide scaling translation factors in the different spatial dimensions. So here, the mesh will look very similar, but the X and Y labels have changed, so the position of the nodes have changed because I shifted the complete mesh by 500 meters along the x-axis and by 25 meters along the y-axis. Another modifying method would be scaling. So I can call the scale method of each mesh, and I can say, okay, the x dimension stays the same, but I want to exaggerate the vertical dimension. And that would, of course, keep in mind that this will also affect the mesh quality. So you could look at mesh quality before and after the mesh modification. Another thing is rotate, which takes the vector of the rotational axis, and this is defined in radian. So I'm using the degree to radian numpy function here, and I'm rotating by 20 degrees. And this will just put a little tilt in my model, so slope, for example. And another form of mesh modification is extrusion. So I can take a surface topography, so just a line, a one-dimensional mesh, and can extrude it into the subsurface into a two-dimensional mesh, or I can take a two-dimensional mesh and extrude it into the third dimension. And this third dimension is provided here, so just takes a numpy array with different positions in this added dimension. And then I'm rotating it here again, just to show you that, that this method we used before, rotate, also works on a three-dimensional mesh, because keep in mind, this extrude mesh on a 2D mesh will produce a 3D mesh. And we can visualize this with the help of PyVista, so make sure to check out Bain Sullivan's tutorial tomorrow, where you will learn much more about this wonderful software package. Okay, So I will conclude with the message that everything I showed you, so creating geometrical objects, creating a mesh, also applies in 3D. In 3D, our mesh tools are a bit more limited, so we are looking forward to any contributions in this area. But again, we have this read mesh IO, where you can basically read any type of mesh format, and we are very much looking forward to the subsurface integration. But everything else here, so we have, instead of create rectangle, we have create cube, create cylinders, so some three-dimensional objects. But we can also add them together, as we did with the two-dimensional objects. We can call create mesh on them. And we also have the same modifying methods, rotating, scaling, and everything we did for 2D is equally applicable to 3D. And this would just be a three-dimensional cube and this cylinder added together. And yeah, with that, this concludes this first part. And Thomas will now use the geometry which we just defined to show you how to simulate something with it.
Yeah, thanks, Florian. Now we have some nice meshes. We can work with those meshes. And what we're going to do is to switch to the next higher level, which is the lowermost level, is the equation level. So doing modeling on equation basis. And what we're going to do is here to model the steady state heat equation. It's a very simple equation, and we want to use the previously created mesh, associate some surface properties to solve a Poisson type equation with finite elements, visualize the results, and do some interpolation stuff. I'm also starting on the scratch. We're using here the heat equation, which is a Poisson equation of this type. So the divergence of a gradient multiplied by some factor A is equal to some right side. For the heat equation, this can be translated in the unknown temperature is depending on a heat source F on the right hand side and a thermal diffusivity, and it's just a continuity equation. It's just the same as in DC resistivity, where this is the electrical conductivity and this is the potential. On the right hand side, we have the current density, but we also can do this on the on modeling Darcy's law. Then this would be the head, and this is the hydraulic conductivity, so it's a very simple equation. We want to model this only steady state. So A is the thermal diffusivity that we will use now. We will not place a heat source because this will mostly lead to the non-stationary stuff. But what we want to look at is to play with different boundary conditions, theoretically or Neumann flow boundary conditions. So we start up with a notebook as follows. So we again import pygimli as PG, and also the show mesh function. There's just another way of using functions like those from pygimli import viewer. What we want to do is to resolve by finite elements, and there's a very easy entry point is pg.solve, which is solving the partial differential equation here with a function solve finite element. We're going to have a look at this on the website. So this is a very generalized model of a parabolic partial differential equation. So we have a parabolic term of a change of a variable u. Then on the right hand side we have an elliptic term, just as I showed you before. But there's also a Helmholtz term and a right hand side source. And additionally, we have boundary conditions on this boundary value problem. So we can have Dirichlet boundary condition, we can have Neumann boundary conditions. So Dirichlet, we are specifying the value of u on the boundary, whereas a Neumann boundary condition, we specify the normal derivative, but we also can combine them into mixed boundary conditions, and two different types of doing this. So you can dive into this a little bit more, but we're going to back to use this pg.solve with a mesh that we created before. So what we're going to do is to load the mesh that we've created before. So we just use the convenience function pg.load, and if you look into your data folder, you can see there are several files that we're going to use for this tutorial, and there's the mesh.dms that Florian just saved. And we just use it, and we just load it from here. Print it. Oh my god. it's data, of course. So it's a mesh consisting of 1,300 nodes and 2,600 cells. And here we want to show mesh. The mesh, that's what we did before. So the mesh is looking like this. We're going to get rid of this output here. What we want to show is the markers. Now we see the markers, which is both the cell markers in the subsurface going from 0 to 3, but we also see the boundary markers, and those will come into play right now when we do the modeling. So we just have to remember the top boundary is marked by a boundary marker -1, and all other boundaries are marked by a boundary marker -2. If you want to show the mesh additionally, we can easily look into the signature of the show mesh, and then we can say show mesh yes, show mesh equals true, and then we see both the markers and the mesh. Then we want to populate those cell markers with some values, with some subsurface values. That's why we are creating a map of a thermal conductivity of a thermal diffusivity A. We'll just create a map, which is a list of mapping objects. So we're just saying, well, we have a region 0, which is the middle layer, and we just give it the value of 1.0. Then we have a region 1, which is having a thermal conductivity of 5, which is a bit higher, which is the top layer. Then we have the lowermost layer, which is having the highest thermal conductivity of 10, and then we are having region number 3, which is the blob here, and in this blob we get an even higher thermal conductivity. And we're gonna use this. If we look into show mesh, we can not only specify a mesh, we can also specify some data that are populated with this. So those data can be a long vector equaling the number of nodes, number of cells, but it can also be a map. So what we're going to do here is to visualize the map thermal conductivity, and we see here's the image of a thermal conductivity. So we have a value of 1 here, a value of 5 here, a value of 10 and 20 in uppermost. So if we want to do, we could also look at this in the log scale. If this property is meaningful to be looked at the log scale, and then we can just do it, and then we have a log scaling of thermal conductivities. Okay, those are the ones that we are going to use. And for the next step, we have to define some boundary conditions. So I'm specifying this via a dictionary object. So the first part of a dictionary, the key, is called directly, and this means we are specifying directly boundary conditions, and then the value of this dictionary is again a dictionary where we specify the boundary marker of -1. You remember it's the top surface with a value of 5. So we have 5 degrees on the top, and we have on all boundaries we have 12 degrees on the bottom. Now we're gonna call pg.solve. What we need for this is the mesh. Then we need a conductivity. Then we need some boundary conditions. And we have an all function, mostly a verbose flag that is telling us, please tell us something what you're doing. And this is using the mesh. This is doing some assembly, and this is solving the system, which is of course very, very fast because that's easy. And now we're gonna show the result. So we again use the function show mesh, and we use this function. We get some message here, and to make the plotting equal for the next time, I'm using a few more options. So I'm using the data T. So I'm showing the temperature here. I'm giving it a label. I'm using a different color map. I'm using for temperature using the hot map, which is very nice. And I'm saying I want to have 11 levels of the control lines, and I want to show the boundary. So now we see the boundary here with black dots, and we see the temperature, which is 5 degrees on the top, and it's 12 degrees on all other sides. So we see our boundary conditions are sufficient, and there's an almost constant temperature in the top layer because the thermal conductivity is so low. Then in the second layer the temperature is increasing, and then in the top layer it's in the bottom layer it's constant again because the conductivity is high, and this is the same also for the blob here. Just to show you some different boundary conditions, I'm going to use a mix of directly and Neumann boundary conditions. So in this type, I'm only using theoretical boundary conditions on the top, which is 20 degrees on the surface, and in all other boundaries, I use a Neumann boundary condition, which means some outflow, it's a negative number, some outflow on all the other numbers, and I'm going to compute this. Now we have 20 degrees on top, and we see there's some outflow almost perpendicular to the boundary that we see in the subsurface. Okay, I'm going to go back to the original problem, and what we want to do now is to do some post-processing. Actually, we want to have a look at the heat flow. So for drawing streams or streamlines, there's a function called for streams that we import from pygimli.viewer. And then we call again the same showMesh function that we used before, but at this time we return the axis and the color bar to it. So every show function has got two return arguments, which is the axis that we plot. It's a matplotlib axis in the 2D case, so we can plot whatever we want to into this axis, labeling, placing dots or text or whatever. And the second one is the color bar, and in this axis we are additionally plotting some streams, and we're going to proceed with we're going to call it with a mesh, and the temperature is generating the streamlines of this temperature field, and now we see it here in the subsurface. It's not only the temperature field, but we also see the heat flow, how it's going to the surface and how it's entering the boundaries of our mesh. Okay, next thing is very important feature is interpolation, because we often want to work on different meshes. We want to go to some different program, and that's why we often want to interpolate our models, our properties to some other stuff. So what I'm doing now is to create another mesh. So far we only have worked with triangular prism meshes, but now we are going to generate a grid. I already prepared some vectors. So I'm generating a grid which is going from -25 to 25 in 1 meter steps, and also from -25 to 0 in 1 meter steps. And I'm going to show this grid. For this, we see we need to import NumPy. And see this grid down here. Actually, we want to have this temperature distribution on the grid. So what we're going to do is to retrieve the temperature on the grid, and for this we are using PG interpolate. Again, we can look into the doctrine, which is quite large because there are many different ways of doing interpolation. And we use an input mesh, which is our mesh that our solution is existing, and then we have some output, and this could be the grid, but we can specifically interpolate the results onto the cell centers. So we are interpolating to a point set which is consisting of a cell centers, and here for showing we use the same plot as before, but only using grid and T grid here. Now we have what we usually do in inversion. We have a constant temperature in each cell because it is because the temperature distribution has been interpolated onto the cell centers, and this is representing the distribution of T on the grid. But you can also do something something very similar by just making a copy of this. Now we are gonna interpolate not on the cell samples, but on the cell nodes. Now we have again a contour line representation like before, but the solution is now living on the node. So we have the number of nodes for the T grid instead of the number of cells. So this could also be different kinds of interpolation. Interpolation is basically included into the finite element, because finite element operator is an interpolation operator. And what else could we do? We are very often are interested only in a small amount of the data. So what we can do right now, and I'm going to copy this, is to produce a temperature log. Maybe we're interested in how's the temperature behaving along this line at x equals 0 down the line. So what we're going to do is to produce an NumPy vector which is going from 0 to 25, and then we are doing a list comprehension of positions. The x position is 0, and the z position is minus d, because z counts upwards, and so we have minus d, and we run through those steps and generate a position vector, and then we interpolate not on the grid but on the position vector, and all the rest is just plotting. So I'm just plotting this temperature curve on the depth axis. We need for this is matplotlib5 plot function, and we import this as PLT. So it's in the ready-made notebook, but I just forgot to call this. Well, if you like, you can add a grid to it so that you can see the temperature behavior. So now we have a temperature depth log at position x equals 0, which is starting at 5 degrees. Upper boundary then is constant, because it's a constant conductivity. But then there's another gradient in the second layer. Then there's another gradient in the third layer, and this is basically the second layer has a lower gradient. Then we have the body that we're diving through. So we have the layer 1, layer 2 going from here to here, and layer 3, and this is the body. So basically we see the thermal diffusivity in the gradient of a temperature depth log. You can see the whole notebook if you're just clicking on the whole notebook, and there's some additional stuff on numerical accuracy. If you want to solve an equation on a highly refined mesh, then you can go into this one. But I will stop right here, and now we switch to Traveltime forward calculation.
Okay. So we will continue with the first geophysical method. So Thomas showed you the general equation level, where you can come with your own partial differential equation. But for the geophysical problems, we have a lot of ready-made forward operators. And the one we will be using here is Traveltime modeling. And the steps we need to do is reading the geometry, same as Thomas used for the heat equation, so the one that we defined. And that you can also manipulate and modify to your liking. We have to define the sources and the receivers. So where do we actually, where do the rays start and end, and where do we take the travel time measurements? We need to populate the subsurface with any physical parameters, and in this case it will be the seismic slowness. And then in the end we will simulate, and we will also add noise to the data for our synthetic experiment. You are familiar with these first two lines, importing pygimli as PG, and also the meshtools package. We know this already. What is new here is now the Traveltime module. So all the physical submodules are in the physics submodule, and we will be using Traveltime and then ERT later on. And we give this the shortcut TT. And we will start by reading in the geometry. And so Thomas used the mesh already. And I still need to modify geometry a bit. So I'm not using the final mesh, but the geometry that we saved. And it's in your data folder, and it's called geometry.poly, and we can read it with the read PLC function, and you also have a link to the documentation up here. So let's make sure that it looks the way we intend it to be. Yes, that's our geometry. For a Crosshole setup, I will just scale it a bit to have something more narrow. So this is just dividing the width of our model to 30 meters in total. So the first thing we need to do, we need to specify our sources. And for doing that, we will import the NumPy package, and we will define the sources and receivers as a NumPy array of positions. So let's say we have 10 sensors, so geophones and sources in each borehole. So let's define the one borehole. Could be defined like this. So 10 rows, meaning 10 receivers, and 2 columns for X and Y position. Then I'm already scaling this by 10 meters to make it the right borehole. And I need to specify the Y coordinates. So everything is homogeneous. So we have the X coordinates are the same. Everything is 10 meters. But for the Y coordinate, we need something that is changing, and it will be changing from a little bit below the surface, so minus 0.5 meters, down to minus 30 meters. Remember that our total depth here was 25 meters. And we want n positions, so 10. Okay, so let's have a look at this. A two-dimensional object with X and Y positions. And now I will do the same thing for the second borehole. So I'm multiplying this by 2. And I'm scaling the X coordinate. So move it to minus 10 meters, while the Y coordinates stay the same. So if I'm doing that, and I'm just looking at the first 13 positions, we see the source is fired at X equal to 10, and then at all depth levels. And then we have the second borehole. Okay, and now we want to visualize the sensors, and we can do this by the plot command. So we can use, let's visualize the geometry first. We can call pg show on our geometry, and this returns the matplotlib axis, and we can draw additional things on top of that axis. So we are just using the plot method to plot our sensors coordinates. So X positions and Y positions. And let's make it red dots. Okay, so these are my sources and receivers, left and right from the anomaly that we want to image. So I just defined them in a NumPy array. What I need to do now is I need to add them to the geometry. So I'm iterating over every position in the sensor position that I have defined. And for every position, I'm calling our geometrical object. And this geometry has a method called createNode. And I can hand over the position to it. And what I also need to do, I need to create a mesh on top of this geometry. So I'm calling the createMesh function again that you're already familiar with. We use some sensible settings like quality 33.5 and an area of 1. And look at the resulting mesh again. Okay, So it looks as expected, but note that if I plot the sensor positions again on top of that geometry, you would see that they coincide with node positions now. For the forward modeling, it's not totally necessary, but it's necessary to have accurate travel time simulations. Okay, so the next step would be to populate our subsurface with parameters. And Thomas showed you the way how to do this with on a region basis. So if I'm saying markers equal to true here, and maybe also show mesh equal to true, we could use these region markers 0, 1, 2, and 3 again to populate the mesh with properties. But we could also do this on a cell-by-cell basis. And this is very flexible, so you could, for example, read in a simulation output out of a flow and transport simulation and reuse that to calculate the geophysical response. So we will do a NumPy array of velocities. And here I'm using 5 entries for 1, 2, 3, and 4 entries. Sorry, 1, 2, 3, and 4. So these 4 entries with 800 meters per second, 500, 1,000, and 2,000. And I'm mapping this with the cell markers. So the mesh contains many different methods. And we have full flexibility, so we can also iterate for every cell in mesh cells, for example, and print the cell center. And I'm just doing this for the first 5 to not have too much output. And for every cell now we could do another for loop and iterate over the nodes, so we have access to all the entries in this mesh object. And we also have access to the mesh cell markers, and this will map our 4 values now to all the cell markers. And this only works because the Python uses zero-based indexing, and we have the marker 0 within that mesh. Otherwise, you would need to account for that by subtracting 1 here. Okay, and this has more than 1,000 entries, and this coincides with the number of cells. So if we print the mesh, we see that we also have 1,380 cells. And to check if everything was mapped correctly, I'm plotting the mesh against our vector that we just created, and we see our subsurface model. So this would be the label that I can provide. We have the PG unit with some predefined default, so this would be the default for velocity in meters per second. Okay, so now I have the mesh, I have added the sensors, but I haven't specified what do I really want to measure. So where do the rays start and end? And for that we have a convenience function, which is called create crosshole data, and it takes the sensor position and it basically provides the rays of every possible combination between the boreholes. And this returns a data container. And you can think of a data container a bit like Pandas data frame. So it comes with different columns, and you can see the entries here. So it's labeled data, and we have G for the geophones and S for the sources. And we also have the sensor positions. These are also part of the scheme file. And now we will iterate over sources and receivers. So S and G again, source and the geophones. And now I'm iterating over these 2 arrays. So every shot and geophone position, which makes up 1 ray. And if I'm just maybe looking at the first 5 of this, okay, so This does not work. Yeah, let's look at all of them. You see that these are just the connections between the sources and the receivers in the right borehole. And these are not the actual physical ray paths. Keep in mind that the ray paths are also dependent on the model, so it's a nonlinear problem. And Thomas will show you this later. So this is just the connection between the geophones that we use for the measurements. Okay, so now we have everything, and after the break, we will talk a bit more about managers, and Thomas will introduce you to this Traveltime manager during the inversion. Here I'm only using one function out of it, and this is the simulate function. And the simulate function takes the mesh we already created. It takes the scheme that we created before, and it takes the subsurface properties, so the slowness values, which would be in our case here 1/v. We can also specify the velocity, but you have to name the right keyword argument. Okay, and then other important keyword arguments here are secondary nodes. These are additional nodes placed on the edges, so on the lines in 2D and on triangles in a three-dimensional tetrahedral mesh, for example. And these allow the rays to pass through the cells at different angles, so it increases the accuracy of the travel time simulation. I'm using 4 additional nodes here on every edge. I'm specifying a noise level, which would be 0.1%, and we usually define the noise for travel time measurements in absolute terms. Could be a triggering offset, for example. This would be in the same units as we have the data, so in seconds. And then we can also provide the NumPy seed to create the Gaussian distributed noise so that we have this reproducible for our research work. Okay, and this runs, and yeah, I should have saved it. So this would be the data, and this will again provide me with a data container. So the scheme that we put in here was also a data container, but it did not contain the actual data yet. So just the sensor positions and the measurement schedule. But if I print this data container now, I see that it has an additional column, and these are the travel times. And you can also extract each column and do some post-processing with it. Here we have a function in the travel time module to calculate the shot and receiver distance, and you could use the simulated travel time here, so the data t, to calculate apparent velocities, for example. And yeah, I'm just finishing with this plot showing the apparent velocities at each geophone and depth position, and you see that apparent velocities increase with depth, which is also coinciding with our subsurface model. Okay, that was everything on travel time modeling, and we will continue with the inversion side of things after a little break until 10 after. So in 7 minutes. Okay, so thank you all for watching this first half, and see you in the second half.
Okay. Welcome back. I hope everyone enjoyed some fresh air, some fresh coffee. We're going to proceed with what we did before with travel time. Now we want to do some inversion of this data, and I want to show you some introduction to the to the method managers. So we are now at notebook number 4, and we're going to start from scratch again. So what we have before is data sets. So what we want to do is learn the method manager and the way they work. We want to invert those data and play around with some inversion options just to get a feeling how pygimli is working and what we have. Okay. So we started with the typical import stuff, and then we're starting to include the data. For this, we load in the mesh. We're using the Traveltime module TT, which is also a convenience function load, and we're going to load in the data traveltime.that, and we can print this data, see what's in there. So we have 20 sensors, we have 100 data, 10 by 10, 2 times 10, and then we have different fields in the model. So we have the geophone field, the shot field, the geophone field, and we have the model travel times t. But we also have the error in the column error here. So what we're going to do is have a look at the data, because we haven't looked at the data itself. So we could easily include a nice function. In pygimli, there's a lot of nice functions. You can explore them in the viewer function. In the LPA, there's a function called show vec matrix, which is doing nothing else than showing vectors in a matrix form. So we're going to generate some data pseudosection or something like this. So we could show vec matrix, and we're going to use this data. So on the x-axis, we take the shot number. On the y-axis, we take the geophone number, and on the value table, we take the travel time. We provide the import. So now we have a plot of our data. So the data are the travel time data t. On the x-axis, we have the shot number. On the y-axis, we have the geophone number. So the first one are numbered from 0 to 9, and the others are numbered from 10 to 19. Actually, we would like to have some more plotting, so that's why I generated a nice function for it, which is also showing the same metric, but instead of numbers, I'm using the depths. So I'm indexing the geophone numbers and shot numbers with the depths and showing this vec matrix, and we're going to pass all quarks, our keyword argument that we have, which is, for instance, the label. So we're going to plot the data travel time here. So now we have the shot depth in meters, which is 0.5 to 23, and we have the geophone depth in meters, and we see the highest travel times occur where the shot and the geophone are very low, and the lowest travel times occur in the middle, where our fast velocity plot is residing. So we can see something already in the data. We could, if we don't have noise on the data, we could also do this right here. And I'm going to do this right now. We could add some additional noise. Let's say we want to include 0.1 milliseconds of additional data. So what we are going to do is to have a look at the data. And we're using the time winner and adding some random noise. Therefore, we're using the NumPy package and NumPy.random, and we're using Gaussian random noise. Remember, we are dealing with L2 inversion, so it's always a Gaussian number. So we're generating a random number of Gaussian rays and multiply it with the error value, which is in this case dt. And finally, we also add this to the error, because now the error has changed. And just add this dt to the error. we don't have errors, we can do this right now. Okay, that's not a big change, but we can look at the Crosshole data now, where they have visually changed. Now we see there's some more error on the data, which is kind of big. But we're going to see whether we can extract something out of it. Okay, first thing we need for an inversion is a mesh. That's why we are creating a regular grid mesh. So we have generated the synthetic data with a triangular mesh, but we are not going to use this mesh. This is an inverse crime to use the same mesh for the inversion as for the forward calculation. So that's why we're creating a new mesh. And I've prepared some x and y vectors, which is going from the minimum of our data positions to the maximum of our data positions in x, using 15 steps in this case, and the same for the y data. And then we're going to show this grid that we generate by the convenience function create grid of x and y, and we're going to show this here. Now we have this grid. We're going to see our sensors. That's why we are going to add something more. But additionally, we are returning again the axis and color bar objects and plotting the sensors with red markers on it. And then we see the mesh. So we have the leftmost borehole here, and we have the rightmost borehole here, and we discretize the subsurface into rectangles, and all rays should go in this model, so we don't need any outer space that we have in the forward calculation. Okay. Now we're gonna proceed creating a manager. We call this manager MGR, and this is a Traveltime manager. We can initialize this already with the data, and we can see what's in the manager, and we can explore a little bit which kind of stuff do we have in the manager. So we can apply some mesh externally. We can check our data. We can check our errors. We can create a mesh automatically. We can draw ray paths. We can access forward operator and inversion objects, meshes, and everything that's in the inversion is inside this manager. So we won't go into detail right now in this tutorial, but we can use a few of those functions like show result and show ray paths and whatever. So this manager is the final entry point. Once you have initialized this, you can access everything that's in the data, in the inversion results, in the inversion itself by the manager object. The main thing that we are going to use is the invert function. So we're going to invert the data, and we're going to use the grid that we have previously generated. And well, I could also give a starting model. Let's say we're inverting right now for the slowness. So actually we're using a starting model of 1000 meters per second, but this could also be different. I could start with using a gradient model. This would be typical for a fraction size mix, but in this case I don't need a gradient model, and I can also specify some additional options, like the secondary nodes that Florian showed. And I'm choosing 3 secondary nodes. I will show you what this means. And I could start the inversion. Now I have a problem. So this shouldn't happen. Okay. So it seems like our additional error was a bit too high. So we're going to start from scratch again, reading in the data. Almost noise-free data than the noisify data. So we have data that are both looking at the data. So we have Traveltime data that are below 1. Two is to use a data filter. And we're just saying data t is smaller than 0, or maybe smaller and equal to 0, and filter them out, and then showing the Crosshole data again, seeing whether there are all data remaining, and we see a lot of data have been removed. Obviously, I did something wrong when typing. I'm sorry for that. Oh yes, there's something I did terribly wrong. I typed a plus instead of a minus. So adding data, I don't want to multiply data. Now we see the noise on the data is not very big because I decreased it. So I'm doing it again with smaller noise. So about this time. This is the noise-free data. Now I'm adding 0.1 millisecond to the data and for the Crosshole data, and now we see noise a little bit increased. And now we're gonna see that nothing is filtered, but our inversion should be running. Actually, the inversion was telling us that there are Traveltime data below 0, and this shouldn't happen. So now the inversion is running, and I apologize for this inconvenience. So we see the inversion has been running, but we don't see any output. So again, like above, we suppose is true. And we see some output. We see the Traveltime for the modeling object. We have a linear data transformation on the data. We have a logarithmic data transformation on the model. Then we're going to see the course of iterations, and we're going to start with a chi-square of 11, and it goes down to almost 1, as it should be. So now we are entitled to look at the inversion result, and we just type manager show result. And we have a result of our final velocity. Note that it is automatically converted to velocity. What you can see if you compare this to the synthetic data, we see the low velocity layer over here. We can almost see the higher velocity layer here, but it's really badly resolved. But what we can see in the middle is a high velocity blob here. But what we can do is play around with inversion a little bit, and for this I'm going to add the show result directly after the inversion result, so that we can play a little bit along with this. So we can change the regularization strength by the parameter lambda. So we can use a very high regularization strength for the inversion, and we're going to see in a few iterations that the model will be very smooth, but with a very high regularization, we cannot reach the data fit of chi-square 1. The model is very smooth, so we can further decrease it to 100, which is probably the default value that we have used before. So now we see faster decreasing. We're reaching 1.6. So we are reaching chi-square 1. So actually, we are going below chi-square 1, which means we should increase our model, because otherwise we are overfitting the data. And now we should reach a point where we actually end up in chi-square 1. So we could do this automatically. There's also a scheme where we optimize this parameter so that chi-square 1 is exactly reached by section. So we are increasing and decreasing the model until we really reach chi-square 1. We could also use A-curve methods, and there's a lot of stuff in there. So now we are again pretty much close to the value of 1. And we're going to show the result, but again we are going to give back the axis. And what we also can do is to use the convenience function show ray paths. And we're plotting the ray paths on the axis, and of course we should also give a model. Just a moment. Show ray path, but actually we want to use the function draw ray paths. Now we see the ray paths going from the shots to the sensors. So the shots on the left-hand side and the sensors on the right-hand side, and we can see that they are not linear, and they are not restricted to the nodes of a mesh, but they are cutting. So they're piecewise linear, but this is what we are controlling with a seg node. So seg nodes, every edge is split into several nodes, like Florian showed you on the triangle before. And if you increase the secondary nodes, the computational accuracy will be increased, but of course at some additional computational costs. And we see the rays are tending to go through these fast blob in the middle, and which we can probably pretty much resolve, at least to the resolution limits that we have regarding our data accuracy. What you usually want to do is to have a look at the data fit, and we can use our previously defined function. So we're going to use a matplotlib subplot, so two subplots next to each other, and they show the Crosshole data once we show the measured data. And the other one, we can access the inversion. So having inversion, then we can access all the inversion stuff. So we can have a look at the chi-square history. We can look at the absolute RMS. We can modify whatever we need, like the maximum iteration number, the model history. We can access the model response and things like this. And we're going to use the model response right here and show it next to the data, which are looking quite similar. So we can visually really nicely explain our data. And that's why we're going to have a look at the misfit, which is the measured data minus the forward response. And for plotting misfits, we are usually using the blue, white, red color scale, so which is 0 center. So that 0 means perfectly matched, and red is above 0 and blue is below 0. And we see a patchy of blue and red values, which means we don't have much structure. So there's only one value here which can hardly be fitted. This could be some outlier in the data, or could be some problem. So we could deal with that with additional options like robust data. This will iteratively reweight the data. So we can have a look at the result. So the chi-square is really very fastly going under 1. And if you look at the misfit, so if we look at the misfit, it is not too much decreasing, but this very single value does not remain. So apparently there's something still in the leftmost sensor, but otherwise the data are really the data misfit is really nice, because this is one important thing that people should look at. Is the misfit, is the histogram of a misfit and the distribution of a misfit. And if we are ending up in the non-correlated Gaussian data of a misfit, we are entitled to look at a model. In this case, we know the error, but in many cases we don't have an idea of the error. That's why for field data it will be very important to look at the data. This is the next point we're coming to, is field data, and we're gonna switch to ERT now. Florian.
Okay, so you saw the inversion, how the method managers are structured, and we used that for a synthetic travel time data set. And now two things will change. We will move to another geophysical method, ERT, and also we will move from synthetic to field data. But you will see that a lot of other things also stay similar. And since we use another geophysical method, we also have to import another subpackage. So we go to pygimli .physics again. And now don't use the Traveltime, but the ERT module. And we will be loading a field data set, which is in your data folder, which is in the Git repository, was acquired at a beach of the island Borkum, northern Germany. And we will use that here as a demonstration. So we will in this data container, and we will have a look at the data container again. We're just printing it, so it tells us we have 81 electrodes this time, roughly 1,500 4-point configurations, and many more columns now. So A, B mark the current injecting electrodes, M and N mark the potential measuring electrodes. We have the injected current I, the measured potential U, the resistance, so the ratio of the two of them, and what we need to process is then the geometrical factors, so that we are able to calculate apparent resistivities. So before we do that, let's have a look at the topography. So the data container also contains the sensor positions, and we can visualize them. We can call the pgx command on the data container, and we're looking at the vertical positions, data again, and let's link them. And to have equal sizing, we set the aspect ratio to 1. Okay, so you see that there's towards the coast, there's some topography, but not much topography. So just these 5 meters over 160 meters. So the topography effect, which we will explore now, will be of minor relevance. The analytical formulas for geometric factors that you know from the textbooks are only valid for a homogeneous half space. So for flat surface, we can also have buried sources for Crosshole setups, for example, but they don't work if we have topography anymore. So we need to recalculate them. Also, if you read in data from an instrument, the instrument does not know about the topography, so it will likely, if it gives k factors, then just the analytical ones. In the ERT module, there's this function create geometric factors. We will have a look at the arguments it takes. It just takes the data container, and we can set it to true, numerical to true, meaning that we will calculate the geometric factors numerically. And this means basically a forward simulation on a homogeneous model with a fine mesh and accounting for this topography. And then we do the same thing again. So I'm copy pasting this line, but I'm setting this numerical to false. So we use the analytical formula. So I'm naming this k analytically. And we do this, and it will tell me that it is restoring the cache. So we have a PG cache operator, which you can put to functions which are of computationally more expensive. So you can restore the output of that function if the input arguments to the function did not change. So if the data did not change here, then it will just give me the geometric factors which it already calculated to save some time. So this is the warning here. So if you don't want that, you need to delete the cache. Okay, and now I'm using the ERT show function. So not PG show, but ERT show. And this will display an electrical pseudo section. And just so that we are on the same page. So in electrical pseudo section, we also demonstrated this here in this little video. I never thought I would be showing a YouTube video in a YouTube video, but life is full of surprises. So you see the measurement schedule to the left, you see the sensitivities, and on the right-hand side, you see the pseudo section developing. So the pseudo section is just a color-coded data table displaying the apparent resistivity, which the subsurface, so the apparent resistivity would be the resistivity that the subsurface would have for this measurement if the subsurface would be homogeneous. And for Wagner and dipole-dipole measurements, these look nicely triangular shaped. Here, this data set was a multi-gradient measurement, so it looks a bit different. And we're not displaying the data here, but as the values, so you can display, define values that you want to display in a pseudo section. You could display the numerical factors, and here we are displaying the ratio of the numerical and the analytical geometric factor, which is essentially the topography effect. Another thing that we need before we proceed with an ERT inversion is the data error. And this is usually done in ERT with reciprocal analysis and fitting a linear model to the error. So this is done in the estimate error function in the ERT module. And it takes the data again, and we can specify the data in absolute terms. So here in a voltage, 50 microvolts, and also a relative noise floor with 3%. And I'm also adding the numerical, more accurate geometrical factors to the data container. So again, this behaves a bit like a pandas data frame. So I can use this create this new column K for the geometric factors and put my numerical K factors in it. And then I will show the data again, but not the geometric factors now, but the errors also within such a pseudo section. So these are percentage errors now. And you also see that there are some higher errors above 10% in the lower part here of this pseudo section. So the ERT data container also comes with a method to filter. So you have ERT filter. Oh, you have ERT remove. No, not ERT, sorry. I'm calling the module I want to remove from the data. So I should call the methods on the data, sorry. So I want to remove from the data. And this can be done for filtering to remove geometric factors or errors or negative apparent resistivities. Yeah, in the interest of time, I will not do this here. I will continue with the inversion. Let's have a look at the data again. And now we want to invert it. And to invert it, we need to initiate the manager. Call this MGR for the manager again. And this is the ERT manager, which I initiate with the data object. And this, again, comes with many different methods. Similar methods that you used before. So Thomas used the invert method to invert the Traveltime data set, and we can use the same method now in a different manager to invert the ERT data set. And so the call would be mgr invert again, and we can specify very similar inversion settings. So we can specify the regularization strength. We could specify a Z weight, so promote structure layering, so have less smoothness regularization in the vertical direction. With this Z weight factor. And this can take a while, so I pre-computed it. And you can show the result with the show result method of the manager. You can specify color bar limits, axis labels. So there are some settings, and you see a very nice inversion result with the water table here. So resistive sediments on top of water saturated sediments, and we also see the kind of a saltwater wedge intruding into the coastal region. So how well does this model, which we have here, it's just the first inversion result, it looks good, but how can we appraise its quality? And one thing we can do, we can look at the fit, similar as Thomas showed before. He had plots of apparent velocity, and we are plotting apparent resistivities here now. So measured data versus model response, we have a chi-square of almost 2, relative error of 5.7%. So this looks quite good, but we want to elaborate it a bit more. So we can have a look again at the misfit, similar as Thomas did it. So we want to be sure that there are no systematic errors in our misfit. We want to have a model which equally well describes the data according to their data error. So I'm calculating here the misfit, which is the logarithm of the model response divided by the measured apparent resistivities divided by the data error. So it's a weighted misfit. And I'm using again the pgshow command, which will detect that it's a data container and it will forward to ERT-show. And we see it's random, so there are no systematic errors. So looks quite good. One important thing here is, I shouldn't have done this. Let me do it. Sorry for that. Okay, I will come back to that later. I have to interrupt it, sorry. Okay, sorry for that. Just a second. Yeah, the inversion takes some time now. I interrupted it. And I will continue from here, hopefully. Yes. So different than from in the Traveltime inversion, we do not only have the parameter domain where we want to estimate parameters, but we also have this bounding region. So I should make this a bit deeper here so that you can, or even deeper, so that you can see it. So in the yellow region, which has the marker 2, this is the parameter domain where we estimate parameters. And the region around it, so if I remove this axis limits, you can see the full extent. This is just an outer region, which is not populated with, where we don't estimate parameters, but we populate it with a prolongation of the parameters with inside the parameter domain, and then it's just used for repeated forward calculations to calculate a more accurate model response. And now we want to modify this parameter domain a bit. So this create paramesh PLC creates a piecewise linear complex. With the data container, we can specify the parameter size. And what I did here is I added this line to the mesh. So this represents the water table. So if I have some borehole measurements, for example, and I have a good idea on where the water table is, and at the water table, I would expect a strong contrast in electrical properties. And to promote this strong contrast, so to allow the inversion to allow the inversion model to have such a sharp contrast, I can reduce or even completely turn off the smoothing constraint across this predefined boundary. And this is what I will be doing here. We will be calling create mesh again with this modified geometry. We will display it, and you will see that this boundary is now part of the inversion mesh. And then we initiate the ERT manager again. Now it's a different type of inversion. It's a constraint inversion. So we give it another name. We call the invert method again with very similar arguments as before. And then we show the result in the end. And you see that this structural boundary, it's just a line that we added to the mesh. But since it received a marker which is larger than 0, it will be automatically picked up by the create constraints method, which will produce a smoothing matrix. And if it finds such structural boundaries, it will disable the smoothing constraints across these predefined boundaries. So this is an advanced type of inversion, which is very similar, but just very simple to realize with these pygimli mesh tools. And we still see the intruding seawater. Okay, and I think that this was it. So we have done the inversion, we have looked at the model response, and we showed how to incorporate constraints into a field data inversion. So, and with that, I will hand over to Thomas again.
Yeah, welcome back to the last notebook. We're going to present very shortly. I'm not going to type this from scratch. I will show the notebook because it's a bit more complicated. But one thing I was really keen on is to show some integration aspects. Is to use how to use an inversion with a custom forward operator. In this notebook, we will show you how to use an own forward operator on with pygimli. With the example of synthetic model for a drone-based control source electromagnetic method. I'm not going to explain this method, but I can give you some links. We're going to invert the synthetic. We're going to invert the synthetic data with pygimli, and for this we are using a really great modeling tool from Dieter, to develop models, which is called MPyMod. The repository can be found at this link here, and MPyMod provides electromagnetic modeling for 1D vertical transverse media with arbitrary transmitters and sensors in 3D. And this can be easily installed by conda install npmod, or even easier with PEP on the command line or in the notebook itself. I already did it. If you just if you want to try it, you just have to type this line, and here we go. Okay. As usual, we import all the necessary functions. We import NumPy, we import the plotting library, and additionally, we are now importing MPyMod. And we're going to use one function. And we first define some settings for the MPyMod modeling that we use. We assume we're having a dipole transmitter on the Earth's surface, which is perpendicular to the 2D plane. So it's going into the y direction with a length of tx length, which is 400 meters in this case. So it goes from tx length divided by 2 to minus tx length divided by 2, has a strength of 1 ampere and everything. And then we're going to have receivers in the air, which are magnetic receivers. And this means they are at the x position, which is a range from 50 meters apart from the source to 500 meters apart from the source. It's a typical setting with 50-meter spacing. And the y dimension is 0. And we're going to the vertical magnetic field, which is the angles here. And this goes into the MPyMod call. And there's some additional stuff that needs to be done for the MPyMod call. We're using different frequencies that we allow. They are between 10 hertz and 5 kilohertz. And for doing so, we define a function which is doing the MPyMod call. So MPyMod is basically only called by the function MPyMod.bipole, and we give all those input data from above using this dictionary, and then we are going to use the resistivity in the subsurface. We're going to use the depths of our layers and at the frequencies. And we're going to have a matrix show this result. I already generated a data function to show, because we're measuring real and imaginary part of the data. I'm not going into detail about this one. What I want to show you is how the data are looking like. So I'm generating a model which is having 3 layers. One layer is from 0 to 100 meter steps, and the second one is from 100 to 200 meter steps, and the resistivity is 100 meter, 100 ohm meter, then 10 ohm meter. So it's a good conductor that we want to detect in about 100 to 200 meter depths, and then 100 meter again. And we're going to call this forward routine, and we're going to see the result as a function of a x position in meters and the frequency in hertz. So we see some imaginary part at a higher frequencies and lower offsets, and this is going to take, we have a shallow conductor. So we want to put this into pygimli, and that's why we are creating a class which is doing the modeling. So we are deriving a forward class from the PG modeling class, and everything we have to populate is an initialization function, and we're saying we want to use a 1D mesh, which is an Occam inversion, and we are going to use the response where we call this previously defined forward operator using mpymod. And then we have this matrix, which is real imaginary part, and we're going to put this into a long vector and stack together the real and imaginary parts. And we also provide a function that is generating a starting model, which is in this case 100 meters depth. Now I'm using this data, the synthetic data, do the same. So I'm making a long vector of it and paste real and imaginary parts together. Then I'm adding some error. In this case, I'm using 1% relative error. So I'm also using a random number like we did before. So the random number of a relative error, we multiply it with a relative error, which is 0.01, and add a 1 to it and multiply it with the data. So every data point will be contaminated with 1% noise. Oh my god. I'm gonna see it. Okay. And I'm gonna define my subsurface model. So what I'm doing here is I'm defining a subsurface model out of 21 layers, going from 0 to 300 meter depth. And I'm initializing my forward operator with a fixed depth, and I'm starting with some resistivity, and I just can do a forward response of a resistivity, and I can print this response. And these are, of course, only numbers right now. We won't have a look at these numbers. But what we know we're going to do is to use this forward operator in inversion. It's as simple as that. We are initializing a pygimli inversion. We're setting the forward operator. You could also pass it directly here. Then what we're doing is to set up a model transformation, which is a logarithmic transformation. So we want to have all our resistivities in the subsurface to be positive, and moreover, they should be above 1 ohmmeter, just to get rid of any problems. And we set this model transformation, and we run the model. It's as simple as that. So we specify in the inversion run, we specify the data, which is the data vector, then the error vector, which is being used for the error weighting, and it's going to specify a starting model of 100 ohmmeters, and we're going to have a look at the data. The chi-square is quite large at the beginning, and it's barely decreasing, but we will hopefully see that it will find some local minimum. Oh my god. Let me see. So so the inversion is very slow, but still steady. Depends a bit. Now we have a drastic decrease of subsurface resistivity. Now we are jumping towards chi-square 1. This is actually what we want to do, is to reach chi-square 1. It's not always so straight, monotonous down. But finally, we end up in a model that is having chi-square 1, so we don't have to care about regularization strength. And the only thing that we want to do is to plot our subsurface model as depth profile. So we're going to plot the model resistivity over the depth. So starting at about 100 ohmmeters, as we did, and then at a certain depth, which is here like 60, 70 meters, the resistivity is decreasing and reaching the value of 10 that we specified. And actually, the synthetic model is looking looking very similar, but we of course end up with a smooth version of the synthetic model. Okay, with this, I'd like to conclude and to have some concluding remarks by Florian.
Okay. So this is where we will stop now, but this is not where you will have to stop. So there's a lot to explore on pygimli.org. We have a lot of tutorials on the basics, on mesh interpolation, on the structure of the mesh. Could also be interesting for if you come from a different package and you want to understand the mesh structure, on modeling, and then also on inversion. What Thomas just showed, how can I bring my own forward operator? How can I do an inversion with it? How can I use more advanced regularization? And many different examples also for the various geophysical problems. So make sure to check it out. If you click on an example, you will always have the possibility to download it both as a Python script and as a Jupyter Notebook. We also very much welcome contributions. So we hope that this tutorial also inspires new users, but also new contributors. And we have a contribution guide here. So you can start by sending us your example, by improving the documentation. If you find something that is misleading, you can also click this improve, this page button in the right sidebar, which will directly bring you to GitHub where you can edit the respective page. You can send us the examples you use. We could put them here in the sections. And if you're more advanced, you could also contribute to the code, which is now made easier because we put the C++ part in a separate conda package, so you can really contribute in the pure Python part over GitHub. And yeah, so make sure to check this website. There's also a list of publications. So if you're interested in who used pygimli so far, let's say for monitoring applications, you can search for different publications and you have everything within this database. Okay, and with that, I'd like to conclude. So we are very happy. We're looking very much forward to your contribution. We will be available today for the rest of the day in the Slack channel. So make sure to post your questions there. And if you're watching this later, you can also contact us at mail.pygimli.org. And yeah, we also hope that we will be able to have such a gathering in presence at some point in the near future. So thank you very much for watching this.